Hi, everyone. Welcome to lecture one of this workshop. And today we're going to give you an introduction to geometric invariant theory, which will be the theoretical basis on which we're going to be building in the next 4 lectures. Okay, on this lecture and the next 4. All right, so an overview of what we're going to see today. Today we're going to see the definition and lots of examples of group actions on vector spaces, their orbits and orbit closures. And then we're going to see what kind of geometric questions one can ask once in this setup. And then we're going to focus on on one particular question, which is the null cone problem. And we're going to just talk about scaling algorithms for them, okay? And then we're going to conclude. All right, so group actions. So let G be a nice group and V be a C vector space, okay? Be a complex vector space. So here, the definition of nice is a little bit technical. So let's just stick to finite groups or SLN, right? So here, what I wanted to think about is think of G as one of the following. Okay, so we can have the group of permutations Sn, or like the alternating group An on n elements, or we can think of it as being the SLN, okay, which is the set of all matrices A, right, like complex n by n matrices, such that the determinant of A is equal to 1, or we can also have GLN, which is the set of all matrices A, which are n by n, such that the determinant of A is actually different from 0. Okay, and we're going to denote so let me just say here that we denote like C n by n. We're going to refer to C n by n by mat n, which is the set of all matrices of n. Okay. And another group that we can think about is the special torus group, okay, which is the set of matrices A in, well, let me just start writing in the new notation, which is n by n matrices, such that A is diagonal. Okay, so diagonal, and determinant of A is equal to 1. Okay, so in particular, you can write A as A1 up to AN and zeros everywhere else. Okay, so think of G as being one of those groups. Okay, and now what is a group action? Well, we say that a group G acts linearly on this vector space V if the action of G respects commutes with the linearity of the vector space, right? So if I have G here is an element of the group, right? And this circle here just means that G is acting on a vector and is an element of the vector space V, then it just means that this action commutes with the linearity on V, okay? So it means that those two sides are the same. All right, so let's see some examples of like nice groups acting linearly on vector spaces, right? So if I have here G being the permutation group and V being the set, being just the space like C to the N, right? We can have that a group action, so a permutation, let's say that pi is a permutation in S and N, and then we have the vector V, which is going to be V1 up to Vn. What we have is that pi acts on V by sending V to the following vector. V, well, let me say sigma here because pi will be a bit harder to write smaller. So sigma, and then we have sigma inverse 1 up to V sigma inverse n, right? So this is certainly a group action, right? And also, sorry, I forgot to say, right, that, well, the group action here is also associative, right? So this action respects if I have G, H, acting on U, right? It just respects the group structure, right? So we have U, this is equal to G acting on H acts on U. Okay, so we have this law as well. It respects the law of the group and respects the law of the vector space, right? So here's one example of a group action on a vector space, right? You can clearly see that this action is linear because if I have two vectors and I add them, right, the permutation, the same permutation will permute exactly the same coordinates, right? So, all right. Another example is just if I have AN is the set of even permutations, okay? So this is the set sigma in Sn such that sigma is even, okay? So this set of even permutations, okay, can also act just by permuting the coordinates, and AN is just a subgroup, right? So we know that AN is just a subgroup of the symmetric group. So there's also the same action that we talked about in example 1 works for example 2, right? And another action, which now we have like a continuous group as opposed to a finite group, is the linear transformations of a homogeneous forms of degree D. Okay, so if you think of a polynomial like in two variables, p, x, y, which is homogeneous of degree D, we can write this polynomial in the following form. We can write this as a naught, or maybe let me write p naught. Like, let me write both coordinates. So x to the 0, y to the d, plus p1 x to the 1, y to the d minus 1, plus p2 x squared, y to the d minus 2, and so on, all the way up to pd, which is x to the d, y to the 0, right? So this is a homogeneous polynomial degree D, right? So let's just put here homogeneous polynomial of degree D, and the PIs are over the complex numbers. So the PIs are each of them in the complex number. So, and a homogeneous polynomial, okay, we go by the usual term that we call them forms, okay? And here you can see that we can associate to each polynomial, we can associate the vector. We can associate the vector, oops, sorry. We can associate the vector p naught, p1 up to pd, right? And this is in c d plus 1 because we have d plus 1 coordinates, right? And now what is the group action here? So the group action here is if we transform, so let me just move this over here. And so the group action now is I can take my variable, if I take any 2 by 2 matrix, okay, so let me save some space here. Let me write it in another. So let's say that A is a 2, or G, right, our element of the group. G is a 2 by 2 matrix. Well, is in SL2, right? So is a 2 by 2 matrix with determinant 1. We know that, let's say we can represent G as A, B, C, D. And then we know that if I multiply G by X, Y, what I get is exactly AX plus BY and CX plus DY. So I get a linear transformation of the variables X, Y. And now what I'm going to do is I'm going to say that the action like G acts on the polynomial P, okay, is the same. And if I consider this as a vector space, what I'm saying is that the image of this will be exactly P evaluated at G inverse, or let me say G transpose, like G transpose X, Y. Okay, and this is just to preserve, and this is just because we want to preserve multiplication, like the associated, the transpose here is just because we want to preserve the the property of the group, right? Like the associativity in the group that we had before. That's why we need the transpose there. Okay, so you can see that this transformation here induces a linear transformation of the coefficients. Okay, so I'll leave that as an exercise. You can see that this induces linear transformation of the coefficients. Transformations of coefficients. Okay. So now you can see that if we take the transformation of the variables x, y, and in that transformation of the variables we have a transformation of the polynomials, we can see that this is a linear transformation. So let me just actually work out an example for us to see here. Okay, so let's work out an example of this action. So example, let's say that d is actually equals to 2. So in this case, we can represent any polynomial x, y by a x squared plus b x, y plus c y squared, right? So in particular, we can associate p to the vector a, b, and c, right? C to the 3. Okay, so now we have this association. And now let's say that we have the matrix here, alpha, beta, gamma, delta, which is going to act on P. So in particular, well, let's say that let's call this G transpose right away, right? So then we know that the action of G on the polynomial P is exactly what? I evaluate P on, if I take G transpose times x, y, what do I get? I get exactly alpha x plus beta y, gamma x plus delta y, right? And we know that the determinant of G is equal to 1, right? So P here, it will become P of alpha x plus beta y and gamma x plus delta y. Now, if we evaluate this, we can see that this will be what? This will be A. Now, A is going to be multiplied by alpha x plus beta y squared plus B, which is multiplied by alpha x plus beta y gamma x plus delta y plus C gamma x plus delta y squared. Now, if we rewrite this as, so we want to rewrite this, okay, as, so let me put what we want. So we want to rewrite this as A prime x squared plus B prime xy plus C prime y squared, because this is the new image, right? Because then we have that GP will be associated to, instead of A, B, C, we'll have A prime, B prime, C prime. Now let's see what this A primes, B prime, and C prime will become, right? So in this case, if we collect everything, we have that the above is going to be equal to, if I just isolate x squared, I have alpha squared A plus alpha gamma B plus gamma squared C. And now if I isolate the xy terms, what do I have? I have 2 alpha beta A plus, now we have alpha delta plus beta gamma B plus, plus 2 gamma delta C. And then we have the last term, which is y squared, which will be equal to beta squared A plus beta gamma, no, beta delta B plus delta squared C, correct? So now we know that this first term here is A prime. The second term is B prime. And the third term is C prime. And note that A prime, B prime, and C prime are linear functions. Of A, B, and C. So this action is linear. Okay, so this is the example that we just discussed. And now let's see another example, which is a little bit more familiar to us all, which is just I take a matrix G, and the action of G on a matrix A, right? So this is a matrix in SLN. And this is just a matrix, like any matrix, right? And this action here is just the left multiplication. Okay, so I'm just going to multiply by G times A. And this multiplication here is actually the matrix multiplication, right? So matrix multiplication. Right, because both of them are the same dimension, so this multiplication is well defined, right? So this is the usual just left multiplication. And you can see that this is a group action as well, right? And we're going to see interesting facts about this, that many objects that are familiar to you fit into this whole theory of geometric invariant theory. Okay, and another transformation like action that is very familiar is the conjugation action. And here what we have is an element of GLN, right? So this is in GLN. And then we have G acts on a matrix A. So A is just any matrix. And it takes the matrix A to the matrix GA, G inverse. Right? So this is the conjugation action. Okay, which should be familiar to us all. And now this other action here, this is called row column scaling, and it turns out that this action is quite special, and it's called, like, it goes by the name also of matrix scaling. Okay, and we're going to be seeing this matrix scaling, analyzing this matrix scaling problem quite thoroughly in the next lecture, and we'll see that it has a lot of applications in many parts of mathematics, including combinatorics. Okay, and here, what is the action? The action, now I have two matrices, right? So I have matrix X and Y, and this will act, maybe let me write like L and R for left and right. So, and now L and R will act on A by left and right multiplication. Okay, so here the multiplication will be L, A, R transpose. Actually, because they're diagonal, I can just say L, A, R. Okay, and this is the regular matrix multiplication. And each of these elements, they are elements of STN. So what are they? So they're diagonal matrices, if you remember, diagonal matrices with determinant 1. Okay, so this is the matrix scaling action, which we're going to be seeing quite often in this course. And another one, which has a lot of has a huge importance in combinatorics and also in complexity theory and algorithms, right, is the graph isomorphism action. And what is this action? So here you can see that our group is again the permutation group Sn on n variables, and V here is the set C to the power of n choose 2. Now, what does this encode, right? So if you think of a graph H on the set of vertices n, and there is a set of edges E. Okay, so here's the set of vertices, right, and the edge. Now we can associate to each edge, right? So we can associate to each edge, like ij, an order, right? So we can associate to each edge ii is a ij is a coordinate of the vector space V, right? Like for any ij, like for any I different from j, right? How many pairs of vertices do we have? Well, we have exactly n choose 2 pairs, and we can say that each of these edges will indicate, each edge ij will indicate a coordinate of V. And now we can think of the graph V as being the vector 1e inside of our vector space V. Now, what is this 1e, right? So 1e, if you look at the coordinate of this vector, if you look at the coordinate ij, right? Maybe let me put the vector like ue here, ue. So if I think of ue as my vector, the coordinate ij of my vector, maybe let me represent the coordinate this way, like ij, the set ij, right? This is equal to 1 if ij in the edge set E, or 0 otherwise. Okay, and you can see that now, what is the group action here? The group action, what it does is that G just permutes the vertices, okay? And when G permutes the vertices, we have the action, the induced action on the edges, right? So let me just put another page here and we can go over this action so you can see that this group action just encodes. Okay, well, that's just encodes. Okay, so we can see that this action just encodes the graph isomorphism problem, right? So again, let's just take G, let's just take N to be 3. Okay, so we have N is equal to 3. And now let's just take the graph H to be the graph 1, 2, 3. So in particular, the vector that corresponds to H, what is the vector that corresponds to H? Well, what are the edges, right? So let's just describe the space V. So V is the space C, 3 choose 2, which is exactly C3. But here we can index the coordinates of V by, the coordinates of V are indexed by the sets 1, 2, 1, 3, and 2, 3. Right, these are the coordinates of V. And now we can see here that our vector U is exactly the, and let's say that we index the coordinates of V exactly by this order, 1, 2, 1, 3, 2, 3. So U here will be exactly the vector 1, 0, 1, right? Because I have edge, so 1, 2. So this corresponds to 1, 2 being the graph, right? This corresponds to the edge 1, 3 not being the graph. And this 1 corresponds to the vector 2, 3 being the graph. So now the set U is associated to H. Now let's say that we have the permutation. So let's say that we have sigma being the permutation. Let's say here, let's say 1, 2, 3. Let's write it in cycle, in the cycle representation, right? So then what happens is we have this permutation. So what is this permutation doing? This permutation is mapping 1 goes to 2, 2 goes to 3, and 3 goes to 1, right? And what does this do to the edges? So this means that the edge 1, 2 will be mapped to the edge 2, 3. The edge 1, 3 will be mapped to the edge 2, 1, which is the same as 1, 2. And the set 2, 3 will be mapped to the edge 1, 3. Okay, and now what happens? Well, the image of H, so if sigma acts on H, it takes H to what? Well, the edge 1, 2, right, will go 2. So, well, we can just write the graph here. So 1, 2, 3, right? And now what happened? We just permuted the vertices, right? So when we send 1, 2, goes to 2, 3. So 2, 3 is an edge because 1, 2 was an edge in the graph, right? So 2, 3 is an edge because this is the image of 1, 2. Now 1, 3 goes to 1, 2, which means that now 1, 2 is not an edge, and 2, 3 goes to 1, 3, so which means that 1, 3 is an edge, right? So this is the new graph, and therefore we have that the action of sigma on U is exactly takes us to 0, 1, 1. Okay, so this is the action here. And this is the action for the graph isomorphism, right? So in here, what we're saying, the graph isomorphism problem asks, like, given two graphs, like H1 and H2, is there a permutation of the vertices of H1 that once we have this induced action on the edges makes H1 become H2, okay? So this is quite important in logic and computer science and combinatorics, okay? Okay, so now we have seen plenty of examples of group actions, and now let's talk a little bit about the geometry of these actions, right? So let's talk a bit about the orbits. So if I give an element of the vector space V, we can define the orbit of this element as the set of all elements of the form GU when G is in the group, is in our group, right? So essentially the orbit captures all elements like W of our vector space that can be reached from U via the group action. Right? And for example, here, if we have the first example that we saw, right? That G is our space Sn and V is our set like C to the N, the permutation of the coordinates. What is the orbit of an element? Well, it's just the set of all possible permutations of the coordinates, right? So for instance, if we have n equals to 3, for example, what is the orbit of the vector 1, 2, 3? Right? Like, let's write it like this, 1, 2, 3, right? The orbit of this vector is exactly all possible permutations. So we're going to have definitely 1, 2, 3 is in the orbit, right? And then we can say 1, 3, 2. And then we can have also, well, 3, 1, 2, 3, 2, 1. We can have, and then 2, 1, 3, and, sorry, 2, 1, 3, and at last we can have the 2, 3, 1. All of these elements can be achieved, can be reached from 1 to 3 via permutations, right? Now, what is the orbit of the vector 1, 1, 1? Well, the orbit of the vector 1, 1, 1 is only 1, 1, 1. Right? So these are two examples of the orbits, and they're just, you know, the permutations of the coordinates. And here, another example, which we can talk about, which was the action of change of coordinates, right, over forms. What does this encode? This is actually encoding the linear transformations of the roots, because if you remember, if I have a complex polynomial P, right, Pxy is a form homogeneous. So it's a form, right, like homogeneous polynomial of degree D. I can write this as product. Well, there is a PD here, right, which is the coefficient of degree D of y minus lambda I x to the power EI, right? And here, all we have is that, let's say we have I equals to 1 up to t, and we know that sum of I equals to 1 up to t, is exactly equal to d, right? Which is the degree of the polynomial, right? EIs are the multiplicities of the roots, right? And we have here that like lambda I should say the lambda I is different than lambda J. So now, if we write the polynomial this way, what is happening when we have the transformation, right? What happens when we have the transformation like alpha, beta, gamma, delta, acting, if this is G transpose, right? Like what happens when G acts on P, X, Y? This action is the same thing as saying, well, if you remember, this action is P of G transpose on X, Y. But then this, maybe let me put it this way, like maybe let me put it in the same X, Y, right? And this is the same if I write it in the format of the product, is the same as saying, oh, this is PD times I equals to 1 up to T of, now Y will become, gamma Y plus delta X. And then we have minus, let me put it this way, like let me put the bracket here, minus lambda I times X will become alpha X plus beta Y. So now what are we doing, right? This is the power EI. So in particular, this gives us a linear transformation of the roots, because each root now will become what? Will become gamma minus alpha minus beta lambda I. Oops. Will become gamma minus beta lambda I Y minus lambda I beta, sorry, lambda I alpha minus delta. Oops, this is alpha here. Alpha minus delta X. Okay, so this we just did. Each root now got transformed from like Y minus lambda I X to this other like lambda minus beta lambda, gamma minus beta lambda I Y minus lambda I alpha minus delta X. Okay. All right, so we finished the linear transformations of the roots. And now we also have the left multiplication action, right? That's so familiar to us. But here the orbits are a little bit complicated, because one would be tempted to think that the orbits just take the matrices of the same rank to the matrix of same rank, right? So same rank and same determinant. And same determinant. But here it is actually not true, because we have no column exchange, right? So for example, if I had these two matrices like here, 1, 0, 0, 0, 0, 0, 0, 0, 0, right? And this matrix 0, 0, 1, 0, 0, 0, these matrices are not in the same orbit. Okay, so the orbits here are a little bit more complicated, okay? But this is not a reason for us to give up on studying the geometric properties of this problem, right? Certainly, this problem is very important, way too important for us to forget, to give up so quickly. Okay, and here in the conjugation action as well, one would be tempted to say, well, is the orbit the set of all matrices with the same eigenvalues? And the answer is no, because this is the difference between diagonalizable matrices and matrices with Jordan blocks, right? So for example, even if n is equal to 2, we already have the example that this matrix 1, 1, 0, sorry, 1, 1, 1, 0, and the identity, right? They are not in the same block. Right? Even though they have the same eigenvalues. Okay, but it's just because one is diagonalizable and the other one, the first matrix is certainly not diagonalizable. Okay, so all right, but we're going to see a little bit more about these last two group actions later. Okay, so and the other one is the matrix scaling action that we're going to see quite thoroughly in this workshop, right? And here the orbits are quite nice to describe. So the orbits here, they correspond to weighted bipartite matchings, okay? So, and I'll create an exercise on how you can deduce that, okay? So, all right. So now if we give an element U in the vector space V, okay, its orbit closure is defined as, you know, if I just take my orbit and now I'm going to add the limit points of this orbit, okay? So, and the limit points here are over the Euclidean topology, okay? So we can talk about Euclidean topology. And, okay, so, and the limit points here, we can, I'm just going to say limit points in terms of Euclidean topology just because it's more familiar, but for those of you who are also familiar with the Zariski topology, we can just say, well, they're the same. Limit points will be the same with respect to the Euclidean topology or the Zariski topology. Okay, so you can pick whichever topology you like, and let's just add those limit points. Okay, so it turns out now that if we talk about orbit closures, then certain orbit closures already become much nicer. So for example, the example of the conjugation action that we talked about, the orbit closures become much nicer because now the orbit closures, they will intersect if and only if we have the same eigenvalues. The orbit closures are not the same, okay? But they intersect if and only if the matrices have the same eigenvalues, okay? So let me just put a warning. They only intersect, like, so same, like A and B, two matrices, A and B in V with same eigenvalues. Implies that the orbit closure of A intersects the orbit closure of B, okay, is non-empty, but not necessarily the same orbit. So for instance, the example that we gave in the previous page, if we just took those two examples, we know that the identity is in the orbit closure of the matrix 1, 1, 0, 1, okay? But the orbits are not the same because anything in, well, if you conjugate the identity, you just get the identity, right? So the orbit of the identity is, the orbit closure of the identity is exactly the identity, okay? So that's why the orbits are not necessarily the same. Okay, so, all right. And now let's go to the second part. So now we saw a little bit about orbits and orbit closures, and we can see that orbit closures are a little bit nicer geometrically than orbits, right? And now we're going to talk about geometric questions that one could ask about orbits and orbit closures.